Hi everyone, my name is Binghang Yuan. I'm a PhD candidate from Computer Science Department, Rice University, and this work is done under the supervision of my advisor, Dr. Chris Sherman. And here we will talk about how to abridging source code. So I'll first discuss why we want to do this research. What is our motivation? So nowadays, if you use any search engine to search a keyword and you carefully go through the result returned by Google, you will figure out that Google uses a kind of automatical text summarization technique that it goes all the contents in the page and automatically select the most important or most relevant sentence to describe that page so that the user can click that page and before the user click that page, the user can have a high level idea of what each page talks about. For example, if I search binary search by Google and say the second term returned by gigs for gigs, it tells me binary search is search a sorted array by repeatedly dividing the search interval in half. So this is pretty cool. But what about search for source code? I tried the same thing on the most popular open source repository management page set, which is GitHub, and I searched binary search, and basically all the returned result is based on the parade text match. There's no technique to automatically summarize a piece of code so that I'll say piece of code so that I can understand the high level idea about this kind of the logic of that method or class. So this motivates our research. We want to remove the trivial statements from the source code so that all the important part is kept intent and so that we can display the source code in a small space and does not compromise the ability of a programmer to comprehend the code. Note that this can be a very important part and integral part of any code search engine. Here is an example. This is a very classic function in the famous merge sort algorithm. Given an array stored two sorted array, index from the lower index to middle and from middle plus 1 to higher index. We want to merge it into a single sorted array. So the most important logic in this algorithm is nested inside this while loop. Thus, as if the checked value I is the value from the left side is smaller than the value from the right side, we're going to move the element from the first array one step forward. Otherwise, we will move the element from the second part one step forward. So what will our tool to handle such an example? It will only keep the most important while loop as is the most important logic in this method, and here's the result returned by our tool. You can see this most important logic is kept in this method. Alright, so within this paper we mainly have this three contributions. The first one is that we formalize this source code abridgment problem as a constraint optimization problem. Then we use a supervised learning approach to automatically determine the parameter for this constraint optimization formalization. And finally, we conduct a very comprehensive user study which gives strong statistic evidence to show the utility of our tool. Now I will talk about our methodology, and I would like to split that into three parts. The first part is about the formalization of this problem. Then I will talk about how we use the supervised learning procedure to determine the parameters for this formalization. And finally, I will talk a little bit about the feature engineering. What kind of feature we choose for this formalization. So, all right. So first of all, in this paper, we focus on abridging Java methods, but the methodology can be easily adapted to any similar programming language. So here we view a Java method as a graph. So the nodes are statements, and edges represents the dependency between two statements. It can either be a data dependency or a control dependency. So then each statement include a feature vector xi, which either from static program analyze or from the text information nested in the statements. Then you can imagine we have magic feature with omega, so that the inner product of this feature vector and omega measures how informative this statement is. So I'll talk how we choose the feature vector at the end of this methodology introduction. And then based on this, we view the abridging the source code as to choose a set of statements that maximize the sum of this inner product subject to a group of constraints. I'll talk about the constraint in the next slides. And note that such kind of constraint optimization problem can be easily solved by any integer programming solver. And it's really first for in our setup to abridging kind of source code with 200 lines only requires a milliseconds level of time to produce such results. Okay, so what are the constraints? So we include three kinds of constraints. The first is called hard constraints. Hard constraints includes the dependency between two statements that cannot be violated by the code abridgment. So for example, if I have two statements, statements I and statements j, statements I have a dependency on statements j, which is encoded by the hard constraint. Then if statements I appears in the abridgment, statements j also must be appeared in that abridgment result. In our experiments, we decided to use the control dependency as the hard constraint. I'll explain this a little bit later with an example. Another kind of constraint is called the soft constraint, which includes the dependency we tend to, or say we would like the abridger to keep. But if it does not, we still accept such kind of results, but we will put and penalty terms in the objective function. And in our experiments, we choose the variable declaration dependency as the soft constraint. And finally, the last constraint is called line count constraint, which means that a user or an application provides a bound of the line counts range so that the abridgment will generate a code summarization with the line counts forced into that range. All right. Here's the example to illustrate why the hard constraint is important. So this is a very simple Java method. I'll return a string based on a random number generator. If the random number is 0, I will return rock. Otherwise, if it's 1, I will return paper. So otherwise, I'll return scissors. And here, if I don't follow the control dependency and removes statements in line 5, statements in line 6, and statement in line 7, here is the result. The problem is that this abridgment will mislead the user. in this case, the user will think, well, if the random number is 0, it will return paper, but which actually the program returns rock. So this is very bad. So we would like to include all of the control dependency as the hard constraint. So finally, with all those definitions, we formalize the problem in this way. The optimization problem tries to find a binary vector where each value represents the related statements should be kept or removed in the abridgment result. So if it's 1, it indicates, well, this statement should be kept in the abridgment, otherwise this statement will be removed. So here's the objective function. It's very intuitive. So this part includes all the information that was kept in the kept statements, and this information should minus the penalty term because those soft constraints are valid. All of this binary vector should satisfy the hard constraint and the line constraint included in this form. Alright, so we got the constraints, we got the target function, and the value is a binary. It's just some binary value, so this problem can be easily solved by the binary integer programmer solver, as I mentioned before. Okay, so with the help of this formalization, the next step is how can we determine the features necessary for each statement, and how are we going to decide the parameters, or say the magic weights, as I suggested before. So I will first talk about how we choose this magic weights. So we can assume we already determined the feature. Actually, this is an algorithm parameter selection problem, and we use a supervised learning approach, which means we ask an expert to manually truncate a diverse set of programs as the training set. Then we use the G-core distance between the manual label and the automatically abridgment generated by our formalization. Then we add the L2 regularization term to prevent overfit. And so with this definition, we have our loss function, and we have the training set, we have the loss function, and naturally we can have the best parameter for this to fit the training set best. Note that this is a kind of different than the standard statistic machine learning task, because the gradient descent won't work as the results, the binary integer integer program solver itself, which requires an optimization procedure. So we use a local search approach to define this optimization within optimization procedure. In our experiments, we use param LS as the local search approach. It generates very good results. And the next step, we will talk about our feature engineering. So the high-level idea is that we want the abridger to decide which statements are more important than the others based on computing the feature vector, the inner product between the feature vector and the magic weights. You know how we determine the magic weights. Now the missing part is the feature, how we choose the feature. So we applied a very standard feature engineering step, that is, we examine the abridgment results given a feature set, and then we try to add experience to add new features and return the model and examine the G-core distance again, which is a kind of approximation of the performance of our source code abridger. And if that value goes down, it probably means our abridger did a better job. And we keep doing this and keep seeing the distance goes down, and by adding new features. But one potential risk is that this will probably let the abraser to overfit our training set. But we apply the standard cross-validation machine learning approach, and at the end, as I mentioned before, we conduct a comprehensive user study to verify the utility of our tool. So as a result, I would like to say we choose the statement type, the parent statement type, and nested level in the abstract syntax tree, and identify reference count as the feature from static program analyze. We also consider the text information nested in each statement. More details of the features can be get from those details are included in our paper. And finally, with the last couple of minutes, I will talk about how we evaluate our tool. The fundamental question we ask is that, does this abridgment tool described in this paper actually help the user to understand the source code more quickly, more accurately, comparing to simply dump a couple of statements from the source code, or say compared to the original code? So the study was designed to answer this question. So we invited 23 graduate students and postdocs in our department to help us conduct this user study. The sample code was from a very diverse purpose repository, and there's definitely no overlapping between the training set and the programs that was included in the user study. So again, we also define a strawman abridgment, which is that we use our IP formalization, and we do not consider any features. We just let the IP solver to randomly throw a couple of statements away, so that the program will satisfy the line count constraint. Additionally, we also let this strawman abridgment to follow the hard constraint, so that actually this can be viewed as a kind of as the union of the multiple revised program slice, and you can view more details in our paper about this. And we designed two tasks. The first task is that given a natural language description of a desired Java method, we ask the user to select from 5 different Java methods to identify the method that was described by this English description. And the second task is that each programmer is given a pair of Java method and a pair of natural language description. We want the participants to match the description with the source code. And for all these two, we deploy this on a online web page. People just do the experiments online. And here's the result. We calculate the accuracy and time for each question, and it suggests that our source code abraser outperforms both the original code and the result generated by the strawman in both time and accuracy for both tasks. And finally, we also conduct the static analysis to say if the result generated from this tool has some static significance, and we use Bootstrap to compute the p-value for those experiments, and the result turns out to be our experiments has strong static significance. And we also conduct some subjective evaluation to ask if the user tends to use our tool. In the end of this user study, it turns out that the participants likes our tools, and more details can be viewed in our paper. Finally, I would like to give a brief summarization for our work. We propose a novel approach that automatically abridge a Java method so that the code can be displayed within a very small place. And we design a supervised learning approach to determine the parameter for that optimization problem. And we conduct user study to show the utility of our tool. In the future, there's still some work. The first, I will like to evaluate this tool in more scenario. Let's say there's different kinds of software engineering tasks, probably as debug or let a user to learn the usage of a new repository, new code space. We believe our tool can help in that scenario as well. And another detail is that we want our tool to automatically determine an appropriate abridgment portion given a piece of source code. And definitely we can try to consider more features and try different optimization formalization for this task. All right, that's all. Thank you very much.